And we're off to the races, lesson 10-7, the final lesson in chapter 10. And you guys, when you get to this finish line, we're going to be ready to take the test. So, joke of the day, math humor. It's called humor. Question, what do you call two unrelated activities scheduled on July 4th? Answer, independence events. We're going to be talking about independent and dependent events. Today's objective for lesson 10-7 is finding the probability of independent events and finding the probability of dependent events. Let's look into this. Our vocabulary for the day would be those two phrases, independent and dependent events. And we're going to develop an understanding of those and a working vocabulary. Adam's teacher gives the class two lists of titles and asks them each to choose two to read. Adam can choose one title from each list or two titles from the same list. So here we have the list of books, and one title from each list would look like this. Choosing a title from one list does not affect the number of titles to choose on the other list. These events are what we call independent. But if we were to choose two titles from the same list, this changes the number of titles that can be chosen from the same list. These events are dependent. Events are independent if the occurrence of one event does not affect the probability of the other, meaning taking away one of the sample spaces. Events are dependent events if the occurrence of one event does affect the probability of the other. Let's look at example 1. It says classifying events as independent or dependent. Tell whether each set of events is independent or dependent and explain your answer. You select a card from a standard deck of cards and hold it. A friend selects another card from the same deck. Are those independent or dependent events? The fact that you kept the card out and then your friend picked from that same deck would indicate that you have a dependent event. Your friend has fewer cards to pick from. The event of her or him choosing a card depends on you picking one and keeping it. How about part B? You're going to flip a coin and it lands heads up. You flip the same coin and it lands heads up again. Independent or dependent? We call this an independent event. The results of the first toss doesn't affect the sample space for the second toss. We have a clean slate. It's either heads or tails the second time. You guys check it out. Example 1 says tell whether each set of events is independent or dependent and explain why you think so. Come right back here and we'll check our answers. So looking at the first problem, a number cube, meaning a dice, lands showing an odd number. It's rolled a second time and lands showing a 6. Well, the first time we rolled it, we don't take anything away from the dice. It still has 6 sides for the second event. So we call these independent events. The result of rolling the number cube the first time doesn't affect the result of the second roll. One student in your class is chosen for a project, and then another student in the class is chosen. The second picking of a student depends on the first one because now we have one less student to choose from. It says, suppose an experiment involves flipping 2 fair coins. The example is on page 741, right below the independent and dependent events, the student-to-student talk. She wants to talk to you about probability. So right below that is this picture of sample spacing. The sample space of outcomes is shown by this tree diagram. So we're going to talk about theoretical probability that we discussed in lesson 10-7. Determine the theoretical probability of both coins landing heads up. The first coin can be heads. The second coin can then be heads or tails, followed by the same example, only flipping a tail first, followed by heads or tails. Determine the probability of both coins landing heads up. So we collect our sample space, and we can see theoretically that one time out of 4, these are the 4 events in the sample space, there's only one that includes both coins landing heads up. So our theoretical probability will be 1 out of 4. Now look back at the separate theoretical probabilities of each coin landing heads up. The theoretical probability in each case is 1/2. The product of these two probabilities is 1/4. The product, meaning we're going to take them individually, each probability, and multiply to get the probability of the two independent events happening. To determine the probability of two independent events, multiply their probabilities to get your final answer. This is an important part of your notes, the probability of independent events, and this is read: if A and B are independent events, then the probability of A and B happening is equal to the probability of A multiplied by the probability of B. So let's use that newfound formula. An experiment consists of randomly selecting a marble from a bag, replacing it, that's the important key phrase, and then selecting another marble. The bag contains 3 red and 12 green. Well, we want to find out the probability of selecting a red marble and then a green marble. We have to first determine, are these independent or dependent events? Well, in this case, we have replaced the marble that we chose, so the sample space for each one is the same, meaning we have an independent situation because the marble was replaced. So we're going to use our new formula, the probability of A and B, in this case red and then green, is the probability that we choose red multiplied by the probability that we choose green. And remember, we had 3 red marbles and 12 green marbles, so we take those two probabilities and multiply. 3 times 12, they're going to simplify first. 3 15ths is 1/5, 12 15ths is 4/5, and we're going to get 4 25ths. That's the probability of picking red and then green. Coin is flipped 4 times. What's the probability of flipping 4 heads in a row? Because each coin, as we flip it, is independent of the last flippage. Yes, that is a word. Today only. The probability of it landing heads 4 times in a row, we're going to look at that. Probability of heads, 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 heads is each of those probabilities independently being multiplied together. So you can see that we have 1/2 to the 4th power, or 1 out of 16. Now if we made that tree and showed these 4 coins being flipped, we could see the sample space and see there are 16 ways that that can happen. Let's check it out, example number 2. It says an experiment consists of spinning the spinner twice. What's the probability of spinning 2 odd numbers? Well, let's look at the probability of spinning 1 odd number, and we want to come back to, is this independent or dependent? And we can see that we're going to spin it, same spinner, but we're not removing the section after we spin it. We can't remove it, so these events are independent. The probability of spinning an odd, we have 1, 3, and 5, is 1/2. Half of the segments are odd. So the probability of odd followed by odd would be 1/2. 1/2 of the segments multiplied by 1/2 of the segments, or 1 out of 4. Let's look at this. Suppose we have 2 different sets of marbles. Determine the theoretical probability of drawing a red marble and then drawing a second red marble without replacing it. So here we have the red marbles, 3 of them. After the first draw, 1 is removed. That's the event we're talking about. So in the second draw, we can see that the sample space has changed. This means that we have dependent events. So the probability of drawing a red in the first is 3 out of 9, or 1/3. And the probability of drawing a red on the second draw is 2 out of 8, for 1/4. And we have a little different formula for dependent events. If A and B are dependent, then the probability of A and B happening is equal to the probability of A, that first event, drawing the red marble when all of the marbles were there, multiplied by the probability of B after A. Let's look at example 3. A snack cart has 6 bags of pretzels and 10 bags of chips. Grant selects a bag at random, and then Iris selects a bag at random. What's the probability that Grant will select a bag of pretzels and Iris will select a bag of chips? First, we're going to take the event and figure out what's going on. The answer will be the probability that a bag of chips is chosen after a bag of pretzels. So we're going to list all of our important information so we understand what we're trying to get out of this problem. Grant chooses a bag of pretzels from 6 bags of pretzels and 10 bags of chips. So his probability will be 6 out of 16. Iris is then going to choose a bag of chips, 5 bags of pretzels now, and 10 bags of chips still. We're going to draw our diagram. After Grant selects, here they all are. He's going to choose his pretzels. The events are dependent because we're removing one of the items from the sample space. So here we have 6 opportunities for Grant out of 16. And when Iris comes up, there's only 15 bags left, but she has 9 out of 15. Grant selects a bag. The sample space changes. The events are dependent. So here's what we're looking at mathematically. The probability of pretzel and chip. We write it the probability of pretzel multiplied by the probability of chip after choosing a pretzel. 6 bags of pretzels from 16. Iris selects one of 10 bags of chips from 15. So we can see the 2 probabilities. We multiply those together and we get a 1 out of 4 probability. Let's try check it out. Example number 3. A bag of 10 red, 12 white, and 8 blue marbles. 2 marbles are randomly drawn from the bag. What's the probability of drawing a blue and then a red? Well, let's understand what we're looking for. The answer will be a probability that a red will be chosen after a blue. A blue marble is chosen from a bag containing 10 red, 12 white, and 8 blue. And then a red is chosen from a bag of 10 red, 12 white, and 7 blue. Here's our picture. Drawing our diagram. After the first selection, we know the sample space changes. We have a dependent event. So we write it out using our formula for dependent probability. We find those values, 8 out of 30. Notice the sample space changes in the second part, and the probability of red would be 10 out of the remaining 29. Multiplying together, we simplify to 8/87. Pretty straightforward. Independent versus dependent. And your problem set is on PowerSchool. It's also on Canvas above your lesson.